Today, I want to talk a little about security. I don't have to mention this, but from the name, you can derive that security of an application, and in our context, security of a backend application is one of the most important things that you as an engineer should be aware of. I'm not saying that all the other topics that I covered in this playlist are not important, but security is something which, if you don't pay a lot of attention to, has a lot of destructive effects on your application. Destructive financially, and when it comes to your business, when it comes to your resources, and in turn, everything boils down to money and finance. But security in itself is a huge domain. You can talk about different aspects of security depending on which context you are talking about. We can talk about browser security, which will talk a lot about HTML and your cookies, local storage, all these different components where vulnerabilities can arise. We can also talk about your network security, which means the transition layer with the HTTP, HTTPS, and your encryption, compression, all these components come. We can also talk about server security. I am not talking about backend security, where we are only concerned about our app, our particular code base, and our particular process, which will be running inside an operating system. When I say server security, I mean the operating system in itself. When we deploy a backend code in a server, we deploy our particular application, which runs in a process inside an operating system. So that operating system itself has a security context. You can talk about that also. And obviously, we can also talk about our backend, which means all the vulnerabilities that can arise because of our app, because of the code that we have written in our backend. And if you start to tackle and if you start to discuss security in all these contexts, it quickly goes out of the scope. You don't need to know all these things about security. Of course, it is always better if you are aware of these things. If you are interested in these things, there are a lot of reading materials that you can find with just a simple Google search. But for this video, where we mostly talk about practical things, where we mostly talk about things that are in the context of backend engineering, in this context, we have to limit ourselves to a particular set of vulnerabilities, a particular set of rules that we should follow to ensure security of our application. And the last thing that I want to mention before we start this video is the purpose of this video is not to teach you all the different fancy security techniques in one video, so that you can just go ahead and implement all of them in your application starting from tomorrow. That is obviously not going to happen. As I mentioned, security is a vast domain and you have to do a lot of reading yourself. You have to do a lot of research. You have to build the mindset to build a truly secure application. That sentence itself does not make any sense because no application can ever be truly secure. As technology evolves, as our libraries evolve, as our programming languages evolve, there will always be security vulnerabilities. But anyway, we have to try our best. So the purpose of this video is not to teach you fancy security techniques. As I have already mentioned in my authentication and authorization video, the goal of this video is to make you paranoid about your application, about the code that you write, and give you a mindset to always keep security in the back of your head whenever you are creating any kind of application. So that is the purpose, that is the goal of this video. Of course, we are going to talk about a lot of security threats, a lot of security based techniques to prevent all these threats. We'll also look at a few demos to understand how it works on code level, etc., etc. But again, if I miss some major component when it comes to security, if I miss talking about a major threat or some best practice, then as I've said, security is huge. And as long as you are able to get this mindset that always keep security at the back of your head whenever you are writing code, then I will consider this video as successful. So with that, we can start. One of the things that I have thought a lot about structuring this video is I don't want to list and I don't want to talk about a fixed list of very abstract vulnerabilities because that never works. Instead, what I want to do is I want to give you a glimpse of how to think like an attacker. I don't want to use the word hacker because there is a lot of cringe already associated with the word. So we are going to use the word attacker for this. And the fact is, these attackers, people who wish harm upon your application in any way possible, they don't really care about the framework, the library, the programming language that you have written. They only care about this one question. The question is, where did the developer make an assumption? That is the most important question, and we are going to pay a lot of attention to this question to find out why this question is so important, especially in the context of security. Because every single vulnerability that we are going to talk about in this video, it all comes down to that single thing. A developer assumed that the input coming from the user, coming from the front end, would be clean, or they assumed that the user was who they said they were, or they assumed that the request that they are receiving on their server, on their backend, was coming from their front end, the front end that they are supposed to serve. And they assume that no one would open the network tab like this, and no one will just take a look at the network calls, and no one will try to modify the parameters. Of course, these assumptions, they feel reasonable when you're building under deadline, right? Especially in startups, there is always a deadline. You want to ship features as fast as possible. You want to meet the client's requirements as fast as possible. In that environment, it is perfectly reasonable to make all these assumptions because you are always thinking in the happy path. The user will always fill the form correctly, the way that you are expecting them to. They will always click the right buttons, and they will always navigate your app the way they are meant to. But unfortunately, attackers, again, people who wish harm upon your application, they don't use your app the way you want them to. They try to poke at every single boundary. They try to modify, they try to break every single input, and they try to guess every one of your assumptions. So by the end of this video, you'll have a mental model for thinking about security that will stick with you regardless of what language or framework that you're using. It can be Go, it can be Python, it can be Node.js, it can be Rust. It does not matter. You'll always start questioning this question, which is, what could go wrong here in terms of security every time you write code? With that, let's jump into our first kind of attacks that I want to talk about, which are, say, injection attacks. Now, injection attacks, I'll come back to why we are calling them injection attacks, but they have been around for decades now, and they're still very common, and they all share the same root cause. And once you start looking at the root cause, once you start understanding the root cause, you'll start understanding an entire category of vulnerabilities. So let's start with a very fundamental truth, a very fundamental fact, which is your application speaks multiple languages. So if, let's say, this is our app, and let's say here we have database, this side we have browser, and this side, let's say, we have operating system. We have our app, let's say this is our backend application. And at all times, we have to imagine that our application speaks multiple languages for multiple contexts. When our app, our backend, tries to query some data, tries to insert some data, tries to delete some data, any kind of interaction with data, it tries to speak to our database. It is a kind of interaction, and for that it uses the language SQL. Same way, assuming that our backend also deals with sending static assets like JavaScript or HTML or CSS, then it also speaks these languages, right? HTML and CSS. And whenever our backend needs to perform some task in the context of operating system, let's say it wants to open some kind of file which deals with system calls, which are governed by the operating system, then it speaks the language of shell script, if you're aware of. So of course, there will be other categories here depending on how big your backend is. But the point is, at all times, your backend speaks multiple languages in multiple contexts. And each one of these languages, they have their own grammar and their own set of special characters, their own way of separating commands from data. And this is where most of the vulnerabilities come from. Let's say we are, as a user, we are here because we interact with our backend through browsers, right? Here as a user, most of the time the vulnerabilities arise because a user speaks one language. Let's say this is HTML, JavaScript, and CSS, because we mostly talk to browsers, right? Whenever a user speaking one language tries to cross the boundary of another language, from starting from here, we interacted through browsers and the browser interacted with our backend. And when this language tries to cross the boundary and starts entering this boundary or this boundary, in those cases, mostly vulnerabilities appear. And we'll talk about what we call them, but SQL injection, XSS attacks, these are one of the examples of when vulnerabilities arise because of one user crossing the boundary from one language to another. Because the input from the user in one particular language, they can mean some kind of special command, some kind of special character in the other language. And that is the root cause of most of these injection based attacks. So let's talk about one of the most dangerous and also common injection attacks, which is SQL injection. Okay, for this, let's imagine a simple login page. You have a login page here, you have the email field, we have the password field, and this is running in our browser. This is governed by our browser. This is our front end, and this is going to talk to our server, which in turn is going to talk to our database DB. These are set up. The user enters the email and the password. Your server receives these two fields, email and password. It makes a request to your database to find if the user exists for this, and it checks whether the password is matching or not. If it does, then it returns a response, right? Very straightforward. Now, what we want to do, we want to zoom in on what exactly is the database query here. So let's say this is the database query that got executed. This is the database query. If you are familiar with SQL, that is great. It is a very straightforward SQL query. We want to fetch all the users whose email is matching this particular user input, whatever we are receiving from the user. But if you are not familiar with SQL, this basically means that our server is asking our database that give me the user with this particular email address, whatever email address that the user has sent us through our front end. If the developer who is building this query by concatenating strings here, the way that is done here by concatenating strings, taking the query template and just dropping the user input here inside the query, then we have a huge problem. Now, to understand that problem, let's first discuss the happy path. As I have already mentioned, most of the times we assume the happy path, the users are going to act like the way we are expecting them to. So let's first do that. The user comes, let's say the user's email address is alice@gmail.com. They type their email and they type their password or whatever the password is, and they send it to our server. Now, given this particular SQL query, we paste it here. When our server receives this particular email address, what we do, we take this email and we inject it here. Now this will become alice whatever at gmail.com. The server constructs this particular SQL query, it sends to our database, and the database is able to find a user with this particular email. It returns it, and the server finds the user and allows the user to log in. That is our happy path. Everything works perfect. We don't have to worry about anything. Now let's talk about not so happy path, which is the attempt of our attacker. So instead of typing a very valid email, what the attacker does, they do something like this. They type a single quote, then they type the word or, then a space, then another single quote. Inside there is one, another single quote, equals to another single quote, there is one, another single quote, then hyphen hyphen. This is the input that the attacker types in the email field and they send it to our server. Now what happens? As usual, the server takes this input and inserts it into this whatever template that it is constructing for the database query. In order to understand this, let's go to a DB Explorer, which will be much clearer. This is our template. For the first case, when we are talking about our happy path, this is what it becomes. Let's add a colon here, and here select star from users where email. This becomes, let's comment this out just for our reference, and this becomes after constructing the query becomes alice@gmail.com. This was our happy path. Same way, let's copy template and paste it here. Now let's talk about what the attacker did. After constructing the query, this is what the query will become. We already had a pair of single quotes here, which was added by the server. Now what happens? Inside that, we concatenate whatever the input that we're receiving for the email. Now what the attacker did, first they typed a single quote, then space, let's type space, it was or, then single quote 1 equals to single quote 1, then space hyphen hyphen, right? This becomes our final query. When we take this whole thing and we insert inside our template where we fetch the user information. In order to test this out, let's go ahead and create a table called users. It will have 2 columns. Let's call the first one name with the data type text, and the second one will be email, again text. Let's end the statement here and let's go ahead and run it. This table is created. Now let's insert some data into this table. Insert into users name, email. The values will be first set is going to be Alice with the email alice@gmail.com. The second set will be the name Bob with the email bob@gmail.com. Okay, and this with a semicolon, and let's run this. We have inserted 2 rows, and if we do a refresh here and check in our users table, let me try to increase the font for this data table. Let's make this, yeah, should be fine. Padding also great. Sidebar also, let's increase it, and a little bit of padding. It's too much. Anyway, this should do it. Let's make this a little bigger. Great. Now we have a users table with 2 users named Alice and Bob with the email alice@gmail.com and bob@gmail.com. Now going back to SQL query, if we run this query, this particular query, let's go ahead and run this. We are getting this particular row as a result. Since we are saying give us all the users from the users table where email matches this exact string, which is alice@gmail.com. That's why we are getting this row with all the columns as a result. Now this one is our malicious query, which if you go back to our board, this was our template. And what it does, it takes the user input and inserts it in between a pair of single quotes. And since the user passed this particular statement, which is single quote or 1 equals to 1 and hyphen hyphen, we take that and insert it into our template. This is what the query becomes. And what happens if we run this? Let's go ahead and run this. We got all the rows in our users table, both Alice and Bob, even though the user did not pass any email, but they were able to get a list of all the users in our database, including their email address. Now let's understand what exactly happened here. Now, starting from our template, our query template, this is what it is in the first part, which is select star from users where email equals to single quote, okay, and the opening single quote. After this point, this is the user's input. This is what gets dropped in. And if we take a look at this input, the first character is a single quote. And since the first character is a single quote, what it does, it closes this particular pair. Since we already had a single set of single quote and combined with the single quote coming from the malicious input, now this pair is complete. Now what this statement becomes select star from users where email equals to an empty string. This is the first part of the statement, which is a complete logic. We want to fetch all the emails from our database where email equals to an empty string. Of course, email will not be an empty string in our database, but that's what leads us to our second part of the statement. Then we have an OR statement. And as the name suggests, OR simply means either this or this, right? This first part is the left side of OR, and this one is the right side of OR. So let's take a look at the right side of OR. We have 1 equals to 1, not 1 as a number, 1 as a character, since they are inside single quotes, which basically says that is the string 1 equals to the string 1? And the answer is obviously yes. So this part of the statement becomes true. And then there is another clever part, which is 2 hyphens. And we use 2 hyphens in SQL to comment out whatever comes after that in that line. And since we have a pair of hyphens here, whatever comes after this, which is a single quote, that gets commented out. If they did not provide this pair of hyphens, then this will throw an error because there is an extra single quote here, which obviously creates a syntax error in SQL. Now what happens to our final query? This part was the left part of the OR, and this is the right part of the OR. Now, if you translate it into English, what it means, what it is trying to say is, return me all the users from our database whose email is empty string, which is obviously false, or when 1 equals to 1, which is always true. Since one part of the OR statement is true, this whole statement becomes true. That is the clever part of this injection. And since this whole statement becomes true, this part executes. Now, essentially what it becomes, if we come here, let's say we copy this and we paste it here. Let's say comment it out. If we take this statement, this whole statement, and make this true, and we close it and we run this, then we get all the rows in our database from the users table. And if you want to shorten it even a little more, since this is only a true condition here, which is a constant true, we can take this also and paste it here. Let's comment this out, and we can just go ahead and remove this part. And if we run this, select star from users, which returns all the users from our database. So the idea behind writing this malicious input is tricking our string concatenation logic into taking a set of characters, which when combined with our string, combined with our SQL template, which is selecting a set of users from our database, that creates a constant true condition, which in turn makes the whole statement exclude the where part, and it essentially becomes select star from users. That's why the attacker is able to get all the users from our system with this input, with just a single set of malicious characters. The characters themselves are not malicious. When combined with our SQL template, they become malicious. With just this set of characters, they were able to fetch all the users from our databases. And since in our case, the users table only has name and email, but in a production database, users table usually has a lot of fields like hashed passwords, addresses, phone numbers, and a lot of sensitive user informations. But that is still not as harmful as the next one. So imagining the same statement, the same SQL template, let's get rid of this and let's remove the comment here. Instead of passing this, what if they changed their command and made it more harmful? What they can do, so let's remove this part. This is our essentially the template. Whatever the user passes, we are embedding it inside this. So starting from here, let's say they again did the same trick, which is passing a single quote. Now this part is complete. So whatever they pass in the next part, that becomes their primary attack command. And after this, let's say they passed a semicolon, then they passed this drop table users, and then another semicolon, then again hyphen hyphen, so that this part gets commented out and it does not throw a syntax error, or there are no other conditions after this statement which is messing with their attack command. Now tracing this part, what it essentially becomes, if you can guess, which is very straightforward, this part of the query is obviously select star from users where email is an empty string. That part is not going to become true because email is not going to be an empty string, because usually we have a not a null constraint on our email fields. But this part, this statement, when it's executed, this completely deletes the users table from our database. We'll talk about how to mitigate this. Of course, the first obvious thing is parameterized queries, which we'll talk about just after this. But the second obvious prevention for this is usually in our application code, in our backend code, when we establish a connection to our database, to interact with our database, to perform operations like create, update, delete, and insert, etc. The credential that we use, the user and password with which we connect to our database, that user should only be given permissions for DML queries, which means data manipulation queries. Data manipulation queries as in insert queries, update queries, delete queries. These statements, which are called DDL queries, which is data definition language, which can alter or delete actual tables from our database. Of course, when we run this will return a successful response, which is an empty set of rows, but this part will never run, which means our users table is not going to get deleted. And the reason, as you can see, the query one returns okay, but our users table, even if you do a refresh, it's still there and the data is still present. And the reason it did not run was because we pasted this inside our DB Explorer, which is Table Plus, and it was not from an actual program. Table Plus, whatever driver, since it's proprietary, we do not know exactly what database driver they use for Postgres. But most of the modern drivers, they have all these safety mechanisms so that they by default block these back-to-back SQL statements. So only the first one runs, this one gets disabled, because SQL injection has been a classic vulnerability since decades. A lot of tools, a lot of drivers and database ecosystem tools, they have a lot of safety mechanisms to disable behaviors like that. But if you're using some older version of a database driver, or a database driver which does not have all these security mechanisms, then this statement will actually work and your users table will get deleted. And judging by this pattern, you can already imagine an attacker with the correct set of skills and intentions. They can do a lot more creative attacks, a lot more damage to your backend and your database. They can do things like use union statements to extract data from other tables, other sensitive tables like payment information. They can also use database specific functions to read files from your server's file system. And in some configurations, they can also execute operating system commands through the database. So there is a lot of attack surface here. That's the reason SQL injection has been one of the most destructive vulnerability since decades. Now going back to our initial explanation of what exactly is an injection attack. Mentioned that injection happens when languages cross other languages boundaries inside a ecosystem of browsers, servers, databases, and other tools. Now looking at our SQL query, if we apply that theory here, SQL or SQL, it is a language where certain characters have special meaning. The single quote here we use to represent a string. Whatever comes inside a single quote, a pair of single quote, that is treated as a string. The semicolon here, that is used to separate two different statements. If a semicolon comes inside an SQL statement, that means that statement is over and the next statement starts executing. The double dash here, this means whatever comes after that will be treated as a comment and SQL will not be executing whatever command is there after the double dash. Same way, keywords like or, drop, where, all these things, they have a specific meaning. And when we concatenate our SQL string or SQL template with whatever coming directly from user input. There, what we're saying that we are trusting that the input does not contain any of these special characters, which is of course asking for a lot, and it is an impossible situation. Even if the user input is not malicious, we cannot guarantee that a benign user, a user who is clueless, they will not type all these special characters inside the input box. We are just assuming that it's all data. And that is the essence of all injection attacks. This part that we treated as data and this part which was supposed to be code, but due to the overlapping meanings of special characters, this thing also became a part of our code, which was supposed to be our data. So in a way, if you want to explain the meaning of injection attacks, it all boils down to this confusion between code or data. Treating data as code or code as data. That's where a lot of injection based attacks are born from. So how do we actually fix this? The answer to that is parameterized queries, and they're also called prepared statements. And this is how they look. If we take this statement and copy it here, instead of doing this string concatenation where we are taking two single quotes and we are just pushing whatever comes from the user inside this pair of single quotes. Instead of doing this, what if we remove this whole thing and we wrote something like $1? And while we are executing this whole thing, what we do usually, so let's say we store this whole thing inside a variable cons statement equals to this whole thing. And we also add a pair of quotes here, whether single quote or double quote, that's on you and your language. And while executing, what we do, we have a DB instance or a pool instance, whatever we have, let's call it something like DB, and we call an execute method, whatever your database driver offers, or a query method, a db.query. We pass the statement in the first parameter. In the second parameter, we pass the slots, whatever slots that are supposed to go inside this query. I'll explain that in a bit. Let's say here we pass the user input. Okay, now let's make this a little bit bigger. Let me change the color of this and also the color of this so that we can differentiate what is the actual query and what is the code. Right? Okay. Now the whole idea of parameterized query is to separate the query from the user data. The user data in the sense whatever data that we are receiving dynamically during runtime, during the execution of our program. The data that we do not have the knowledge of while we are writing the code or while our code is compiling. So instead of building one string with everything mashed together, we send two things to our database. Here, if you take a look, this is our DB instance, pool instance, whatever you want to call it. This part will differ from language to language, from framework to framework. So this part we will ignore, the syntax will ignore. Let's focus on this part. This practice is usually common between all kinds of drivers and all kinds of ORMs. So you'll be able to relate this statement. Okay. Now, focusing on our actual query template or our actual query statement. The first part, from starting from here to here, previously where we were concatenating this part with the user input, what we did, we wrote our first part as it is, as it was before, select star from users where email equals to dash. Okay. This part contains no user data. This usually contains the tables that we are selecting from, whatever conditions that we are checking, and whatever operations that we are performing, things like update, etc. And in this case, this is a select statement, no user data whatsoever. Now, the second part comes where we have a slot or the actual values or the place, the slot or the empty box where the user data will go eventually. And we call these parameters because parameters in the programming language jargon means a slot where eventually data will be pushed in, eventually data will be filled in. Now that we have our statement ready, we have a slot reserved here. when we actually execute this statement, we pass these two things to our database. The first part, we pass this whole statement, the statement that our database is supposed to execute. In the second parameter, we pass the actual value. So this user input, this might be coming from a query parameter from our HTTP endpoint. Now we take that and we directly inject it here. And this in turn will be injected in this parameter, this query parameter, or this empty slot. And if we take this statement, let's paste somewhere here with the color this. So eventually this statement becomes this thing. Whatever data, whatever user data, whatever data that we pass into a parameter, now this in turn becomes this, which is let's say the user typed alice@gmail.com, right? This is what the query becomes in the end. The database takes this part, this statement, and it knows that since it encountered a phrase where there is a dollar sign in front of the phrase, it is treating this part as a slot. And what it did, it took the second argument that we passed into the query function, it took that and it injected that into this slot. Now, if you ask what is the difference between this method and the previous method where we were concatenating string, which was more intuitive and which was more easy, in fact, the difference is when the database constructs this query by taking our statement and all the arguments, this part, whatever it inserts into this slot, this is purely treated as data. There is no confusion between data and code, which is usually the source of all kinds of injection attacks. Now that possibility is gone, because if we take the initial malicious statement, this whole thing, let's say we take this whole thing. So now let's take our malicious example for our user input. Let's say the attacker came and passed this whole thing, which is supposed to be a malicious input. And we took that particular user input, and this time we are using parameterized queries instead of doing string concatenation. We took that input and we passed our database the query template, which is this part, and the user input, which is this part, and our database in turn constructs this whole statement. Now what is the difference? Unlike before, when the database encounters this single quote, it does not try to confuse between code and data. It does not treat it as a actual single quote which is going to merge with the existing single quote and it will complete one part of the statement. That will not happen. This will not be a complete statement, because whatever comes inside the slot, it is treated purely as data, or in simple language, it is treated purely as a string. No part of this data will be confused as a command. And that is why this whole thing is now just a garbage string. Since this is clearly not an email, this will not return any kind of row from our database. And also, since we are using parameterized queries, it will not be able to harm our database in any way possible. Of course, you can argue that this particular string, this should not have reached up to this point where we are executing a statement for an email with this particular structure. Usually in our validation layer, we should catch these kind of strings, which means if a string does not have a structure of an email, then the validation layer should throw an error saying that this does not look like an email. This is just a random garbage string. So it will not reach up to this point. But even if for some reason your validation layer is weak or is not as strict, if it did reach up to this point, then our database driver will take care of that. Nowadays, every single database driver in every language supports these parameterized queries. In fact, every ORM also uses them by default. The only way to be vulnerable is to deliberately, if you intentionally bypass all this safety by building raw strings by yourself, which does not even make sense or is convenient in any way possible, that is only when you will be subjected to all these different kinds of attacks and vulnerabilities. So that is your advice for the first kind of injection attacks, which is SQL injection. Always use parameterized queries. Even though this has become such a common practice that I did not have to cover this. Anyway, most people use ORMs and ORMs by default use parameterized queries. And even if you use SQL raw strings, the database drivers also encourage you and make it as easy as possible to use parameterized queries. This has become such a common vulnerability that this did not need covering, but still, if you wanted to understand why this particular type of injection attack has been so destructive for so many decades, then this part would be helpful to you to understand what exactly your database driver does by using these parameterized queries. Now, some of you might be thinking, I use MongoDB or any other kind of NoSQL or document database, and since I don't write SQL, I am safe and I don't have to worry about user inputs, which is obviously again not true. In MongoDB also, queries are represented as JSON-like objects, and when you want to find a user by email in a similar situation like this, you create an object with an email field and the value that you're searching for. And the problem is that MongoDB query objects can also contain operators. Things like not equal operator, the greater than operator, the exists operator, and many other kinds of operators. And these operators are specified as nested objects with special keys starting with a dollar. So a normal query might say find where email equals to this string value. But if the attacker can control not just the value, but the structure also, they can pass an object with the not equal operator. So if your application takes a JSON input from the user and passes it directly to the database query, even though that is an obviously stupid thing to do and no one in their sane mind will do it, but still, if you were to do it, an attacker can inject these operators. So that's also something you have to be wary of, even if you use NoSQL as your database. Of course, if you use MongoDB or NoSQL database in the first place, then you have bigger concerns than worrying about security. On the same note, there is a different type of attack, a different type of injection attack, which is called command injection attack, which works pretty much the same as an SQL injection, but the attack target is, instead of your database systems or your backend system, it is your operating system. In an SQL injection attack, what happens, you have an SQL query template and you take user input without proper caution and without proper techniques. You just add or concatenate the user input with your SQL query and pass that as code instead of treating it as data. The same kind of thing happens in command injection, where instead of an SQL string, you have a operating system command. It can be a system command or it can be some CLI program that you call. For an example, let's say you have a web service, have a web app where you ask users to upload images, and that image in turn goes to your web server where you have to process that image. Processing can be of any type. Let's say the request may be to compress that image, or maybe the request is to resize the image. It can be of any type depending on what you're providing. So your web server takes that image, but in order to resize that image or compress that image, etc., what you do, you use a CLI application or a CLI tool. Something like FFmpeg is a very popular tool for any kind of image or video processing. So what you do in your backend code, after you get the user's file in your handler, you execute a OS function, which in turn calls this CLI tool, which is FFmpeg. And there are some arguments here, something like what is the height, what is the etc., whatever arguments usually FFmpeg takes. And in the end, there is a slot or there is an option to specify the output image file name, something like output.jpg. Now for this, what you're doing, you are taking users input for the name of the output file. So the user has the capability to define what is going to be the name of the output file for the input image. So what you do, you just take the user's input and pass it into your whole command. So which in turn becomes the above command, which is fine as long as it is a genuine input. But let's say you are invoking the same command, mpg height 120, width 220, something like this. And in the end, you're, let's say, -o, and you specify the file name. Here, what you're doing, you're passing the user's input as it is. And in this case, if the user inputs something like this, semicolon rm-rf/, this whole thing becomes the command now. So this thing executes, but when it encounters a semicolon, this is a complete command, and starting from this is going to be executed. And of course, we all know the destructive effects of rm-rf/, which is deleting your whole root folder. The attackers can also get creative. They might use pipes to redirect the output to a different or more destructive command. They might also use ampersands to run commands in the background, which might work as a spyware in your system, in your server system, because each shell, whether you are using ZSH or fish or bash, whatever shell that you use, each shell has its own set of special characters and escape sequences. And someone who has the skill, they can do proper research and come up with more creative exploits for your system. And the fix for this is similar to the SQL injection fix, which is just separate the command from its arguments. Most of these languages, the system languages or languages that enable you to interact with your operating system, whether it is Node.js or Go or Python, whatever language that you're using, they all have these functions that take the command, this part, as one parameter, and the arguments, in this case, the output file name, that in a different parameter. And these functions that are provided by your programming languages or your framework, they pass these arguments, the arguments that are coming from the user, directly to the process without them going through your shell interpreter. When the user's input is passed directly to the shell interpreter, that is treated as code. As we have already mentioned, all these injection attacks happen when our workflow, our system confuses data with code or code with data. So in order to prevent that situation, when we use proper functions provided by our programming languages, these command injections can be avoided, because these functions, they inject whatever user's data directly into the process when the program is already running, instead of interpreting the programmatic meaning of the user's input. They treat it directly as string. So that was a different type of injection attack, which is called command injection. Now let's try to summarize the injection attacks. This is the mental model that applies to pretty much all the injection attacks. Whenever you are passing user input, whatever coming from your user that they type in their keyboard or paste it, whatever user input that you are getting in your server, which is another system. The system where the user types is the browser, and that travels to your system, which is the operating system of the server or your backend system, whatever programming language or framework that you're using. When that happens, whether that is SQL or NoSQL or shell commands, HTML, LDAP, XML, or anything else, whatever you can imagine, you have to ensure that the user input is purely as data. It should never be treated as something that can be executed, something that can be interpreted. And the safest way to do that is to use APIs, use functions, use methodologies that enable you to separate structure from the data, separate code from the data, which in our case, when we talked about SQL injection, they are parameterized queries. And in case of command injection, they are argument arrays, which are provided by your programming languages or your frameworks. Something that you should never do is doing all these kinds of dangerous or sensitive operations using string concatenations or using template strings by mixing user input with the control syntax. So the thing to be paranoid of that I mentioned in the first part of this video is, whenever you're building a string that will be interpreted by another system, and that string also includes any kind of user input, you have to stop and think more about it and always try to find a parameterized alternative to that. And most of the time, it almost always exists. Next, let's talk about authentication. We have already covered authentication and authorization and a lot of aspects of that in the authorization video. But in this part, in this section of this video, we are going to look at authentication and authorization by keeping vulnerabilities in our mind, by thinking about where the weaknesses might be, where people usually mess up. So to give a brief, authentication is basically the process of verifying the identity of your user, to finding out which row exactly in your database in the users table associates with this user who is trying to currently access your system. That is basically the question that we are trying to answer every time we are talking about authentication. So if you get authentication wrong, the malicious user or the attacker, they can impersonate your users, they can access their private data, they can take actions on their behalf, and they can also steal their money if you are dealing with any kind of payment related operations. And these kinds of vulnerabilities, the account takeover kind of vulnerabilities, we see every day in real world. So there are a couple of obvious thumb rules that we can follow where typical vulnerabilities arise so that we can avoid, as backend engineers, these kinds of issues in our systems. But before we dive into the technical details, I have an advice. Since we are talking about authentication and authorization, if you can avoid implementing authentication yourself, and here I'm not talking about avoiding implementing your own cryptography algorithms, etc. I mean, in the general sense, if you can avoid implementing the whole authentication flow, at least in your production systems, then you should definitely go for it. If you have the budget, if you have the approval of your company for the budget of taking an authentication and authorization provider, then that is always a good move, because the obvious benefits, even if you think beyond security, the first thing, it saves you a lot of time. Of course, when your service finally scales to thousands of users or millions of users, you are going to see your authentication provider sending you invoice bills of thousands of dollars. But by the time you reach millions of users, you most probably have a revenue source. So you can anyway handle the auth related bills. But as I was saying, the first benefit of taking an auth provider is the amount of time saved, and in turn the amount of money that you can save on your developer's salary. Because to get the whole authentication and authorization flow right, and when I say the whole authentication and authorization flow, I don't mean a very simple JWT verify and storing the token in your cookie and verifying it. That simple flow is obviously something that you can implement. There are LLMs that can definitely implement them for you, and there is not a lot of difficulties or weaknesses when it comes to security in that flow. But when we are talking about production systems, it is much more complicated than that, and the scope is not as clear as that. Most of the time, when we are talking about the whole authentication and authorization flow in production systems, we generally prefer stateful authentications. By stateful authentication, I mean we can keep track of all the devices where the user has currently logged in, and if the user wants, they can immediately revoke the sessions of all these devices at once. Or if we want, we as the provider of the service, as the provider of the system, we can revoke all the sessions of the user from all the devices and log them out. We have the capability for that. So that kind of capability, that kind of setup is called a stateful authentication. If you want to learn more about stateful authentication, stateless authentication, you can revisit the authentication and authorization video. But if we want to provide a stateful authentication workflow to our users, the things start getting more complicated, because the setup is not as straightforward as signing a JWT, sending the JWT, and the front end storing it in cookie, and your server verifying it with each request. When we talk about stateful authentication, there is databases involved, there are caches involved like Redis. Then you have to think about what is the best place to store users' permission. Then you have to think about timeouts. Then, as I talked about, you also have to think about all these revoking mechanisms, revoking from your cache, revoking from your database, right? That is just one part of the equation, which is stateful authentication. Then comes the social authentication, like sign in with Google, that we see in pretty much all the professional SaaS services, or your service concerns developers, then sign in with GitHub. Mostly all these services, SaaS services, a production SaaS service, it generally provides 2-3 social providers, something like Google, or sign in with GitHub, sign in with Twitter, whatever. So for that, you have to implement OAuth flows yourself. OAuth flow not just in your backend, also in your front end with the redirect mechanism for a very good and very smooth user experience. Once that is out of question, now you have to also implement the system so that your email and password based authentication, which when we are talking about stateful authentication, which is directly concerned with this is directly connected to your social provider authentication, which is your OAuth flow. Which means, let's say I sign in to your service with my email, which is one@mail.com, some sample email, and my password, something like password is ironic since we are talking about security in this video. But anyway, for the sake of this example, let's say your password is password. Now, you as a user signed up to my service using this credential, and you frequently sign in to the service using these credentials. So one day what you do, you sign in instead of your credentials, which is email and password, you try to sign in with Google with the sign in with Google button. When that happens, your auth system should be capable enough that it can connect your email credential flow with your OAuth flow, which is sign in with Google flow, so that it does not treat this user, even though they have the same email, as a different user just because they used a different method of signing. Right? That is another problem. And I can go on and on about a lot of not problems, but inconveniences which your developers are going to spend weeks on, or you are going to spend weeks on if you are a solo developer or you are building your own project. Of course, you can go ahead and cut corners in a lot of these things that is anyway going to compromise with your security or B, with your user experience. You have to make a trade-off on either of these every time you cut corners. So with all these things, the argument always comes down to this. Use a auth provider. They take care of all these things. The modern providers like Clerk, they also provide RBAC, permissions, a lot of other stuff, like advanced security stuff they take care of. Of course, these services, they might also have user experience issues. They might also have vulnerabilities in future, but they are a security company. Their whole service is surrounded around authentication and security. So they have a dedicated security team which thinks about security 24/7. They handle edge cases that you will not think of, and they will respond to new kinds of attacks that come in the market very quickly, since they are spending 24/7 on finding out and fixing different bugs or vulnerabilities. And all these things that I talked about, the different inconveniences that you have to face as a developer, they have already fixed this. And with just a few buttons and with an API key, you can provide world-class user experience to your users for authentication and also world-class security. So in my opinion, it's always worth it to make that trade-off of paying a few bucks for an auth provider instead of going ahead and implementing your own auth flow and dealing with all these things. Of course, let's say when you have thousands or millions of users and your authentication provider bill is crossing, let's say $10,000 or $20,000 bill, then you can definitely consider migrating to your own authentication setup. By then you'll have the revenue, you'll have your developer bandwidth and priorities state. So then you can definitely go ahead and implement your own auth workflow, which definitely makes sense. But when you are starting out, it is always recommended to go with an auth provider. But even if you do listen to this advice and you get an auth provider, you still need to understand how authentication works. You need to know what to configure, what can go wrong, and how to integrate it securely. So that is the reason we'll talk about authentication, different issues in authentication right now. Starting with the first kind under authentication, which is the password storage. So since we are talking about authentication, let's start with passwords. Since most of you will deal with passwords, even if you are using an auth service. So during the time of sign up, a user comes and they enter an email and a password. They hit enter and that goes to your server. Now the question is, what do you do with it on the backend? Of course, when we are talking about server, we mean the backend. And you as a backend engineer, what exactly do you do with it? How do you store it so that you can verify it later when they log in? And for some of the advanced users, this might sound very silly and very beginner developer targeted, but we have to talk about this so that we can understand the reasoning behind the advanced password storage practices that we have today, which are very common in the developer ecosystem. But as a beginner, you might not be aware of those. So the naive approach of storing password is, of course, having a database column with text type, and you just store whatever the user has sent you in the plain text format, right? So let's say the user has passed something like 1, 2, 3, 4, 5. You take that, this is your server, and you store it in your database, right? So that the next time user wants to sign in, he passes the email and 1, 2, 3, 4, 5, which gets to your server. The server fetches the user's password using the email from the database, which is 1, 2, 3, 4, 5. It tries to matches and the server lets the user log in, right? As simple as it can get. But the problem with that is databases get breached every single day. If you follow the tech news or cybersecurity news, every other day you'll see a headline saying that this database got breached and a lot of users' credentials got leaked. And it happens to companies of all sizes, not just big companies and not just small companies. Every kind of company has the same kind of probability to go through a breach. And breaches happen for a lot of reasons. It can be because of some insider employee trying to take revenge on you, or it may be because you are using a third-party service and they got breached and in turn your database got breached. There can be a lot of reasons, but the truth is they do happen. And when your database gets breached and you're storing your password in plain text format, all those passwords are leaked. At that point, you can argue that, okay, the moment you know you have a breach, you go ahead and reset all the credentials of all the users, log them out and ask them to create a new password. But the problem is the moment a user's password is breached, their presence in any kind of internet website is also. The reason being, more than 70% of the users, they use their same passwords in multiple sites, right? They use the same kind of email password combination in pretty much all the sites. A very less number of users use password managers, which randomizes the password for each site. But still a lot of internet traffic, a lot of internet users, they use the password. So the moment your database gets breached and you expose a certain user's email and password combination, the attacker can pick that up and they can run that on a lot of sites. It can be payment related sites, it can be e-commerce sites, it can be social media sites, a lot of sites, and there is a huge probability they will be able to match one of those sites and they will be able to take over that user's account. Usually users are not aware when database breaches happen unless they follow tech news very closely. So that is a huge security risk, storing passwords in plain text in your databases. Even if there is no breach happening, when you're storing passwords in plain text format, that means that your developers, the developers who are working on your system, the developers who are building the backend, they can see those passwords, and your database administrators, they can see those passwords. Anyone with the database access in your system, they can see any user's password in your system. So you're basically trusting every employee, every contractor, freelancer, everyone who might access your systems with all your users' credentials and their online presence. So by now we know that storing passwords plain text in a database is a wrong way to do it. So what is the solution? That's why people have come up with hashing. Now, of course, hashing was not necessarily invented for storing passwords in databases, but hashing is a very good use case for password storage. If you are from a computer science background, you will already be aware of this. Hash is typically a function which is called the hashing function, which is one way. That is the most important tool of any kind of hashing function. And the goal of this hashing function is it can take any kind of string, 1, 2, 3, A, B, C, at the rate, any kind of strings as an input of any length also. The strings can be of any length, starting from length of 1 to length of hundreds of characters. They can take any kind of input of any kind of length, but in the output, the condition is they always have to return a string or any kind of output of fixed length. Depending on what kind of hash that you use, the length will differ, but the condition is it always has to be fixed length. If the hashing function says that it will return the output of 27 characters, then the goal is it does not matter what is the length of our input, the output will always be of 27 characters. And the second condition is for the same input, does not matter how many times we call the hashing function, it always has to return the same output of the same length, right? It cannot be a random function which gives us different output for the same input every time we call it. The output will always have to be same and the output will always have to be of fixed number of characters, which summarizes what is a hashing function. And the last condition was it is always one way, which means we can get the same output for the same input of this fixed number of characters. It does not matter how many times we run the hashing function, but we should not be able to get the input from the output, right? It should be mathematically impossible to get the input from the output using the computing capability that we have at the moment. So given all these features of a hashing function, this is a very good candidate for us to store our password in our database. So what we do, let's say the password is 12345. Instead of storing this particular string in our database, we take the hash of it. Let's try it right now. Let's say search password hasher. The input is 12345. There is a cost factor which we'll ignore and we say generate hash. Gives us a set of characters. Let's say paste it here. Okay. So instead of storing 1235, we pass it through a hashing function. In this case, we pass it through bcrypt, which is a very popular hashing library, and we store this hash in our database. So the next time the user logs into our database, what happens? We fetch the hash of the password for that user, which we have stored in the users table or the accounts table or wherever. We fetch the stored password, the hashed password of the user. Then what we do, we take the user's input for the sign-in attempt. We take that password and we hash it and we try to match whether the current hashed password matches our store hash. If it does, then the user has typed the right password and we let the sign in successful. Now in this case, think about the situation of our database getting breached. What happens? The attacker gets access to all the password hashes of all our users. The hashes of the passwords, not the actual password. And since one of the properties of the hashing function is you cannot, under no circumstance with the computing power of our current systems, get the input from the output of a hash, the user's identity is safe in the internet. The password is never exposed. The attacker under no circumstance can get the access to the actual password. Now that we have discovered hashing, the use of hashing to store our passwords securely in our database, we should be secure safe, right? Unfortunately, that is not the case. Since hashing has become the industry standard for storing passwords in databases, of course, attackers also know this fact. And what they have done is they have built a huge storage of pre-computed hashes. Let's say there is a big table which can be used in scripts like Python or any other exploiting scripts, and this table is basically a one-to-one map. For example, for the string something like 12345 is a common password that people use in a lot of sites. For that they will have a hash something like dollar like map to this. Same way for the string password, will have some other hash. If you do a simple Google search, you can find an image like this. So where you can see there are common passwords on the left side and hashes of those on the right side. So rainbow table is basically a table with common passwords and their hashes. And of course, not every hash returns the same string, the same output string for a particular input. But since usually there are industry standards of which hash is currently the most popular, so attackers can use that particular hash to build this particular rainbow table of common passwords and their hashes. Now, using this, what they can do is, let's say your database gets breached, but this time, instead of storing your passwords in plain text, you have stored them using hashes, and you are all confident that you are super safe. The attackers can never get access to your users' credentials. But again, what happens once the database is breached and attackers get access to all those hashed passwords? One of the techniques that they can apply is taking a rainbow table like this, which has the mapping of all the common passwords and their hashes. They can run a lookup. And when they do that, there is a huge probability that some percentage of your users are using commonly used passwords like password or 12345 or password at 123, all these common passwords. And those attackers, they can get a couple of matches where the hash is exactly the same as one of the hashes in the rainbow table. And since a hash function will always return the same output string with the same number of characters for a particular input, they can exactly reverse map what is the password of the user for that particular hash. And using that, they can find out the passwords of at least some percentage of your users. And that is why you're still not safe even if you just use hashing to store your passwords in your database. So what we can do for this situation is something called salting. Now, what is salting? So far, we have discussed that for each input of a commonly used password, something like 1, 2, 3, 4, 5, it'll always produce the same hash, 5, 6, 7, B, and something of some number of characters, as long as you are using the same hashing function. And since they always produce the same hash for the same input, they are prone to rainbow table attacks. In order to prevent that sameness, what we have come up with is salting. Now, what does salting mean? It is a very simple trick/technique to avoid this sameness problem of same input generating the same output, which is universally. Now, what we do, a user signs up, say with the name a@mail.com and the password 12345. In the first method, what we used to do, we used to store in plain text. Second, we started using a hashing algorithm. By the way, for a long time, bcrypt has been the default hashing algorithm for pretty much all the web apps on the internet. But recently, Argon2 ID has been the industry standard for the most secure and most performant hashing algorithm. That is something that you should know of, and you can do more reading on that on your own. One of the good resources for reading about authentication is Lucia Auth. Lucia has been one of the good authentication libraries with good primitives and a very well-written documentation. But Lucia is no longer a authentication library. Instead, it is more of a guidance towards implementing your own authentication using the best industry practices, etc. So it is a very good resource to understand the mechanics of secure authentication and industry standards. It's something that you can explore on your own to implement secure authentication. Now, coming back, that was the second method where we implemented hashing. Now, in the third method, what we are saying is just hashing is not enough. We also have to integrate salting here. Now, what does salting mean? Let's say the user signs up with these credentials, which is a@mail.com and 12345 as password. Previously, what we used to do, we used to take the password 12345 and run it through a hashing function in case of Argon2 ID and that or bcrypt, and that returned as some kind of hash of some number of characters. Now, in order to prevent the sameness problem, what we'll do, we will add a new element to this, which is a random number. So instead of just passing the password string, we'll also add a salt. And salt in this case is just a string which is randomly generated for that particular user. Let's say this is the user 14 in our platform. So for user 14, we have a database row in our database where we store the user's name, we store the user's email, we store the hashed password. Now we will also store the user's salt. We'll generate a salt. Now this salt has to be generated from a cryptographically pseudo random generated function. You'll easily find all these different kinds of functions from very popular libraries. OpenSSL is one of those. And we have to generate this salt, which will be something like sp3 some string, and we'll also store that in our database. And while hashing, what we do, we take the password, we concatenate with the salt, is a randomly generated string that is unique to this particular user in our platform. Then we hash the whole thing. And after that, whatever we get, we store that in our hashed password column. Now in this new scenario, what happens? Let's say our database gets breached. The attacker gets access to all the hashed passwords and the salt and user's email, everything. But in order to get access to the user's actual password, not the hashed password, previously they used rainbow tables, which had a mapping of users' common passwords and the hashed version of it. Now, when they run the rainbow table against this leaked database, they will find 0 results because each of these hashed passwords have been hashed with a randomly generated salt. So this hashed string will never match any other string in the world. It does not matter even though the common password is 12345 and the user's password is 12345. But the attacker will never get to know this because this 12345, which is the common password, and the hashed version of that, which is in the rainbow table of the attacker, and this version, which is the 12345, is the actual password of the user in our platform. But the hashed version of that has been hashed using a salt, which we have generated randomly. So there is no way these two are ever going to match. And that is how we prevent rainbow table attacks, by using salts and not just a hashing function for storing our password. Now, with the introduction of hashing, with the introduction of salting, we should be completely safe from any kind of password-based attacks. Unfortunately, that is still not true. Now comes another threat, which is the brute force attacks. These days, especially with the advent of all these LLMs and all, GPUs have become very popular, and there are companies, there are manufacturers, there are providers, also cloud providers, which provide GPU instances for some fixed amount of price. Now, modern graphic cards or GPUs, they are very good at computing hashes. A single GPU can compute billions of SHA-256 hashes per second, billions. So even with salting, an attacker with your database can do what's called an offline brute forcing. For each user, they can take the salt and they can try common passwords one by one. They can hash that common password combined with the salt, and they can check the hashed password with the breached hash password. And with their capability of billions of attempts per second, they can even try every password up to 8 characters, every common password pattern, every word with common substitutions within a matter of days. And in order to prevent this problem, we do not use common hash functions like SHA-256 or MD5. These are also hash functions commonly used for file-based hashing to match the integrity of files when we are transferring files over the internet. But we do not use them for password hashing exactly for this reason, because our graphics card computing is so fast at these hashes that they can do billions of hashing functions attempts per second. This is the exact reason we use slow hashing functions, which I have already mentioned. It's called bcrypt or scrypt, or the current industry standard, which is argon2id. These are called slow hashing functions, and they have been specifically made for password hashing. The other hashing functions, the MD5, SHA-256, these are general purpose hashing functions which have a lot of use cases, but these ones, the slow hashing functions, which are deliberately made slower because of the use case of password hashing. They have what we call as a cost factor, or also called as work factor, which controls how slow we want them to be, depending on our system's bandwidth, depending on our system's computing capability. We can decide how slow we want these algorithms to be. So we can decide, while we are hashing our passwords for a new user, we can decide whether we want this particular hashing to take 100 milliseconds or we want it to take 5 milliseconds. That is on us, depending on how much latency, how much computing power we can afford in our system. Now, if you think about it, for a genuine user who is trying to log into our platform with their email, which was a@mail.com and 12345, and we are using Argon, 2ID, or bcrypt for hashing this, and we have decided that we want this particular hashing function to take, let's say, 400 milliseconds, right? So for a genuine user logging in through browser, the login taking somewhere around 400 to 600 milliseconds is not a big deal. In fact, this is almost imperceptible to the user. But for the same scenario, for an attacker, for a malicious user who is trying to brute force his way into our system by taking our breached database and trying out billions of guesses offline, for them, this changes the whole equation, because previously when they could try a billion attempts per second, now it comes down to just 4 or 5 attempts per second, which means instead of being able to crack users' passwords in the matter of days, now it will take them decades or even centuries. The next topic to discuss under authentication is sessions. Your user has logged in and they have provided their email address, they have sent it to your server, you have checked with hashing and whatever authentication mechanism that you have, and you have made sure that your user has proven their identity. Now, what is the next step? We cannot possibly make our users enter their password every time they want to access our platform or every time they want to make a new request. That would be a very bad user experience. So for that, we need to remember that they have already authenticated with our system, with our platform. And this is exactly where we talk about what we call is sessions. When a user successfully signs in or successfully logs in, the server does 3 things. First, it generates a random session identifier. 123 A Z $, whatever. This is a very long random string, ideally somewhere between 128 to 256 characters. And again, it must be generated by a cryptographically secure pseudo random number generator function, which are provided by popular libraries. Why do we need to make this random? Because if an attacker can guess your session ID, if they can guess this particular session identifier, they can potentially hijack any session of any of your users. And by making sure that our session identifier, this whole session ID, is somewhere between 128 characters to 256, even if it is just 128 characters or 128 bits, we are making sure that there are more possible session IDs than the number of atoms in our universe, which means that guessing this number is almost practically impossible. The second thing that our server does is storing this session identifier in our database. Now, this could be Redis, which provides a very fast setting and accessing time, which can provide a better user experience, or it can be your primary database, also something like Postgres or MySQL. With this session identifier, we also store some kind of metadata in our database, again in Redis or our own database. Things like who does this session belong to, the user's information, when it was created, so that we can do operations like timing it out, revoking, etc. When it will expire, our default expiry time, 7 days or whatever, the IP address of the user, so that in the user's dashboard, we can show from which location this sign-in attempt was made, or which are all the locations where the user has signed in, and also the user agent. The user agent, which is basically a request header in our API calls, this tells our server from what kind of device or what kind of browser we are trying to access the platform. So using the user agent, our backend, our platform can know that the user is trying to access from a Chrome browser or a Firefox browser, from an Android phone, from an iPhone, whatever the device type or the browser type is. And the third thing, the last thing, the server sends this session identifier, this cryptographically safe session identifier, to the browser and asks the browser to store it inside a cookie. Now, since this is stored inside a cookie, all the subsequent request that is made to our platform or our backend, this particular session identifier is always sent back to us, to our platform. And for each of those requests, the server extracts the session ID, the 128 character random number or random string from the cookie. It looks up in the persistent store, whether it is Redis or Postgres, depending on your implementation, finds the associated user who has initiated this session, who is the user of this session. And finally, it knows that this is the particular user who is currently making the request. Now, even if you are using JWTs, which have a slightly different format, a slightly different workflow, because they are stateless and we don't maintain the session in our persistent store, but the philosophy of identifying an authenticated user works pretty much the same way as a stateful workflow, which we just discussed. Now, when you are using cookies, there are some flags, there are some configuration of a cookie that we should be aware of, and that is always recommended to be used in a production system. The first one being HTTP only. This means that when we set HTTP only flag to true for this cookie, which has our session identifier, this means that if your site has an XSS vulnerability, we'll talk about XSS in a bit, but it basically means that if an attacker is able to run JavaScript in your user's browser through your platform, through some vulnerability in your site, then your site or your platform is said to have an XSS vulnerability. If you do have that, then some potential JavaScript can read your local storage. So storing your session identifier or storing your JWT tokens in your local storage is always discouraged. That is why setting HTTP only to a cookie, make sure that this malicious JavaScript snippet, it does not have access to this particular cookie. Of course, JavaScript can also read cookies only if HTTP only is not set to true. And that is why it is important if you're storing any kind of sensitive information related to authentication, which is usually a session identifier in case of stateful authentication or a JWT token in case of stateless authentication. It is important that you make this flag only to true, so that JavaScript cannot access your session ID or your JWT token. The second flag is secure. When this flag is set to true, your browser makes sure that this cookie is only transferred back to your platform, back to your backend, only if the connection is HTTPS. It will not try to send the cookie over HTTP or HTTP protocol if TLS or SSL is not enabled for that connection. Now, it is important because HTTP traffic can be intercepted on public networks, on public Wi-Fi or cafes by malicious ISPs, or if the Wi-Fi router itself has some kind of spyware configured, which can read all the traffic flowing through that endpoint, flowing through that hop. So if your sensitive cookie, which has the session identifier or the JWT token, it gets sent over an HTTP connection, can be stolen by anyone who has access to that endpoint, who has set up that spyware, or someone who is observing the traffic with a tool like Wireshark. So the secure flag, make sure that your cookie is only transferred over HTTPS connections, which are by default encrypted. Even if someone is watching your traffic, they cannot make sense of it because everything is encrypted. Third important flag is same site. This flag controls whether this particular key can be sent during cross origin requests. I will talk about what is cross origin, but this can have three kind of values. One is strict, second is lax, and third is none. Okay, what does strict mean? It is exactly what it sounds like. The cookie where we have stored our session identifier or our JWT token, it will only get sent to the domain or the platform or the site where the request is originating from, which is essentially our own backend. So for example, if someone clicks on a link which is a link to your site, but it is hosted on some other site, in that case, the cookie will not be sent because this is essentially not your originating request. It will only get sent if it is a request is starting from your own front end, from your own site. With the same site flag set to lax, what happens? The cookie will be sent for top level requests, which means direct link for your site, but it will not get triggered for other types of elements like images or iframes. We'll cover why we are talking about images or iframes when we are talking about links and requests in a attack class which is called CSRF, which is called cross-site request forgery, which involves making use of images and iframes to trick our server into believing that the request is a genuine request originating from our platform or our site or our front end. So with the same site configured to lax, we are only allowing top level links and not any kind of triggers started from images or iframes. When it is set to none, it is the most relaxed. It is sent for all kinds of requests, but it requires that the secure flag has to be at least set to for some kind of security. So in our case, for storing our session ID cookie, you either want strict, that is the best case scenario, or you never want to make it as none. This prevents this whole class of attack, which is called CSRF, cross-site request forgery, which we'll cover in a later part of this video. Now, with that, talking about cookies, we have covered talking about stateful authentication and the kind of vulnerabilities and the security mechanisms that you have to keep in mind when you are dealing with stateful authentications. Now coming to stateless authentication, where we are primarily dealing with JWT. There is an alternative to stateful authentication or stateful sessions or server-side sessions, which are called JWTs. Now the difference is with sessions, what happens, your server, your database, it stores the session data, the user's information, the IP address, the user agent, whatever information that particular session has, it stores it in the database and it gives the client just the ID of the session. This is just one column of that session row and the client stores that ID, and in every subsequent request our server, our database is able to take out that particular session row by using this ID. Is the session ID. Now, the difference in JWT is the whole session data. This, as you can see, the decoded payload that is shown here in the official JWT site. This is called jwt.io. Here, the actual session data is sent to the user or sent to the front end, sent to the browser, so that for every subsequent request, the user, the client is going to tell us who the user is. One natural question that comes to mind in this case is, if the user is going to tell us, if the front end or browser is going to tell us who the user is, isn't it prone to all kinds of attacks? Like the access is within the user's hand. Now, if they want, they can impersonate as any other user in the platform and tell us that I am not user A and I am user B. So I should have access to user B's account, and a lot of different kinds of attacks like that. Fortunately, that does not happen because of how JWTs itself are constructed and all the different pieces that come together to make a JWT based authentication workflow possible. Now, if we take a look at this particular JWT example, which is shown here, it generally has three parts: the header, which is the first part, which is shown in green; the payload, the middle part or the second part, which is shown in white; and the last part, which is also called the signature, which is shown in purple here. Now the header, it describes the token. It describes what kind of algorithm was used for this particular JWT. The payload contains what we call as claims in the JWT jargon. It is basically some pieces of information that we manually store inside the JWT for all the back and forth transferring that happens between the client and the server. Now, if we take a look inside the claims table, we have a couple of common fields. One is the subfield as per the JWT standard. This is the subject of the JWT, and in other words, the actual user, which can be the ID of the user as per the platform, as per our platform. It can be UUID or any kind of ID that you generate for your platform, for your database. It also includes another field called IAT, which is the actual timestamp when the JWT was created. And using this particular field, our server logic, our server code can decide whether it is time this JWT is expired or not, depending on when it was issued and for how long we are letting JWTs to work. Apart from these ones, the default ones, you can also add your own claims. Claims are just a fancy way of saying key value pairs, pieces of information that you can store inside a JWT. So apart from the default ones, you can also store your own custom claims. In this case, the name of the user is stored and also the information that whether this particular user is an admin or not, that is also stored as a custom claim. Now, the last part, which is in the purple here inside the JWT token. The last part we call as JWT signature, which involves three parts. One is the header, second, the payload, and taking these two and signing them with a secret token. Again, a randomly generated cryptographically secure string. And we sign these two, header and payload, together. And whatever we get, that is the signature of this, the last part. This is how it typically works in case of JWT based workflow, which is the stateless workflow. User comes and provides their email and their password, sends it to our server verifies it, and if the password is successful and everything. Now, in this flow also, we use the same kind of password storage and password interaction mechanism, which is hashing the password, salting the password and everything. That does not change. What changes is the actual session storing and session not storing part. So here, after the password matching and everything is successful, the server creates a JWT which looks something like this with the user's ID and other relevant information, like if they want to store the user's name, the admin, and the issued at field is automatically created by whatever library that we are using for interacting with JWTs. Then the server signs the payload using a string, a random string, which is stored inside the environment variable of the server. Using that string, it signs the payload, and whatever JWT is generated after the signing, this JWT is sent to the client for storing and for sending this back to the server for every subsequent request. Now, client take this, stores it ideally in memory or in local storage in some cases, or in cookies. And for every other subsequent request, the client sends this JWT back in an authorization header. Now, server gets the request, it tries to extract this particular JWT from the authorization header. It verifies the signature. Usually, libraries provide a function called verify, which takes secret key, which is stored again inside our environment variable, and it tells us whether this JWT is successfully verified or not. If the signature is valid, then the verify function will return true, and the server will know that this payload has not been modified or has not been subjected to any kind of tampering. So the whatever information inside this is completely true. Now, looking at this whole flow, one big advantage is the server does not need to store anything inside the database, as compared to the previous stateful workflow where we had to store the session information either in Redis or our database. In this case, everything happens on the fly. during runtime by checking just the JWT claims. And because of this reason, using JWT's scaling is a lot easier because there is no overhead of interacting with a database or caching layer using Redis. But even with JWTs, there are, of course, some of the less favorable properties of JWTs that we have to talk about since we are talking about security. The first one, which is the very obvious and very important one, is revocation is hard. Now, if you think back, if you look back at our sessions example, with sessions, if you wanted to log a user out, what you had to do was simply go into your database and delete that particular session from the database immediate. And the next time the user refreshes or sends any kind of request, the front-end platform should ideally log the user out. But if we talk about JWTs, this functionality, this revoking functionality, at least the immediate revoking functionality does not work as smoothly. You cannot just delete a token from the client. Since JWTs are created and sent to the client for storing it and sending it back to us for every subsequent request, we cannot just ask the client to delete the token from the browser. And in turn, as a result of this, one primary security vulnerability that arises here is if the user's account is compromised. If somehow some other malicious user got access to the user's account and the user sends us as a platform a support query that their account has been compromised and they want us to revoke all their logged in sessions from all devices. Now we are in a difficult spot since we have implemented stateless authentication. We cannot help the user in any way because we don't have the capability to revoke any kind of sessions from any devices. If we had implemented stateful authentication, then we could help the user by logging out of all the devices in a moment's notice. Of course, over the time, after realizing the limitations of JWTs, the community has come up with some workarounds. One of the popular ones is blacklisted tokens, which means that for that particular user, we take that particular user the next time the request comes and we add it as a blacklist to our database or to our caching layer with Redis, and we call that a blacklisted token, which means we will not serve successful responses for any requests that has this particular token attached to it. The second workaround is using short expiration time with refresh tokens. Now, this is a very popular workflow. What happens with this is instead of issuing just one token to the user after a successful login, what we do after a successful login, we issue two kinds of token. One is access token and the second one is a refresh token. Now, the general practice is keeping the expiry of access token to something very short, 5 minutes or 10 minutes, and the expiry of refresh token to something longer, let's say 1 day or 7 days, depending on how paranoid you are, how secure you want your systems to be. And for every subsequent request, the user will attach the access token. But once the 5-minute window is gone, once the access token is expired, technically, what happens? The server will obviously throw 401 unauthorized response code back to the client. And in the client, when it sees that our server has responded with 401, what it will do, it will use the refresh token, and the refresh token is supposed to be saved by the client upon successful login completion, which it will receive from the server. The client will save this refresh token somewhere safe in local storage. And when the access token is expired, the client will send the refresh token back to the server saying that the access token is expired. I need a new access token. The server will check the validity of this refresh token and it will check whether the refresh token is expired or not. If it is not, then it will again issue two sets of token. Again, a new access token and a new refresh token. And the cycle continues after that. What happens with this flow is even if the account gets compromised in some way and the attacker is able to get a hold of the access token, then the session will only last for 5 minutes. After that, they cannot refresh the token since they do not have access to the refresh token. Even if they do have access to the refresh token, again, that will also expire in 1 day. So these are not perfect workarounds, but these are the workarounds that the community and the engineering standards have come up with to mitigate the revocation challenge of JWTs. And another confusion that usually happens is this particular string, which is the payload part of the JWT. This is just a base64 encoded string. If we take this and let's base64 decode, we paste here and we say decode, then we can see the full JSON here. ID of the user, the name, whether the user is admin or not, when was this issued, etc. Of course, we cannot really go ahead and make any change here. Let's try to do that. Let's say instead of John Doe, we remove the E part. So now it's just John Doe, and we take this and let's say we want to encode this. We paste this new JSON and we encode it in the new base64. And let's copy this new base64 string, go back to our JWT, and let's try to change it here. Now, the moment you try to change the payload in the signature part, which is in turn the verification part, it says that the signature verification has failed, which means that the server will immediately know someone has tampered with the payload and this JWT should not be trusted, and the server will not allow the request to go through. But the fact that this string is just a base64 encoded string means that we should not store any kind of sensitive information inside this. Only store those kinds of information which, when exposed to external users or malicious users, there is nothing much they can do with that information. It is only helpful to our server. And the last problem and the most discussed problem with JWTs are the storage. Where should you keep the JWT token when you send it back to the client? Where is the ideal spot for the client to keep the JWT token? Now, local storage is still the most used solution, even though local storage is vulnerable to a lot of different kinds of attacks, since it is accessible by any JavaScript snippet if your site is vulnerable to XSS based attacks. So local storage is obviously not a good choice since XSS can steal it. The second option is cookies, and for cookies again, in order to prevent JavaScript from accessing that cookie, you have to make it a HTTP only cookie, which we just discussed. Now with all this, you are anyway back to our cookie based solution, the HTTP only cookie based session solution. So my general advice when it comes to authentication, when you're choosing between stateless and stateful authentication, is unless you have specific scaling requirements like horizontal scaling, multiple servers being able to authenticate a particular user request, unless you are in a situation like that, always prefer stateful authentication, always prefer sessions. And even if you have scaling requirements, even if you have a requirement where multiple servers need to authenticate a particular user request, you can make use of distributed key value pair based databases like Redis to store the user sessions. That is not a problem. So session based authentication, stateful authentication is always preferred and always advised, as per my opinion, over stateless authentication. The trade-offs of stateless authentication are just not worth it. Stateful authentication or session based authentications are even simpler. The revocation strategy is very straightforward, and the whole workflow and the architecture is compatible with most kind of SaaS projects. But if you do use JWTs, always use short expiration times, something from minutes to hours, not days, and implement refresh token flows with server-side storage, and always use HTTP only cookies rather than local storage. With all these different workarounds, you can make the pain points of stateless authentication go away, but they still feel like hacks as compared to a stateful authentication. One more important piece of topic when we are talking about authentication is rate limiting, a very important mechanism for securing your authentication. without rate limiting, if you have set up your server, what happens? An attacker, a malicious user, they can try thousands of requests per second, per minute, millions of billions of requests for trying different kinds of password, different combinations of username and passwords on your server, on your authentication endpoint. And since you are not limiting the rate at which a particular user can make API calls or send you requests, all of these go through. Now, from this, two things can happen. One, they are able to find a match and get access to a user's account, which is very bad. Or second, they send such a volume of requests to your server that your server cannot handle the load of all these requests per second and your server crashes. This is also bad. So rate limiting is obviously a very important and a mandatory security mechanism for your authentication workflow and also your other endpoints, some kind of global endpoint. And the general practice is you should be more restrictive when it comes to your rate limiting configurations for your authentication workflows, for all your authentication endpoints, and you should be a little more generous when it comes to your other endpoints. So the configurations for rate limiting differs whether it is your authentication endpoint or your general service endpoints. Since we are talking about authentication, it is also recommended to have multiple layers of rate limiting, not just a very simple, straightforward rate limiting strategy for your authentication endpoints. The first layer usually is per IP rate limiting, which means that you limit how many login attempts can come from a single IP in a given time frame. Maybe something like 10 attempts per minute. This will help you stop automated attacks, but there are some problems with per IP based rate limiting, because in a lot of organizations, universities, the outgoing IP address might match of different users who are trying from different devices, because all of them go through the same hop. So that will not give you the correct rate limiting metric all the time. And even if you don't consider that with the modern network infrastructure at current times, attackers have techniques to use multiple IP addresses using things like botnets or proxy networks, VPNs, or rotating IPs. There are a lot of exploiting techniques. So IP-based limiting does not really work to mitigate advanced attacks. So another strategy that you can implement is per account locking or per account limiting, which means you limit how many failed attempts can happen for a single account. So maybe like 5 failures per 15 minutes should log the account for 24 hours unless they contact the support. So this will help you stop attacks that rotate IP addresses or target a particular account. But for this, if the attackers use another clever trick, which is trying one password, let's say something like 1, 2, 3, 4, 5, and they try this one password across different accounts. So one attempt at account A, one attempt at account B, and so on. In that case, your per account limiting or per account locking will not work. And since they're anyway using multiple IP addresses, your first layer of rate limiting, which is per IP rate limiting, that will also not work. And this attack will go through. So for this, the last resort that you can implement is global rate limiting, which means that how many login attempts your system can take in a given time frame, or how many failed login attempts your system can take in a given time. So even if the attacker uses multiple IP addresses and tries a single password across a lot of accounts, and for your global rate limiting, you have configured that in your whole system, in 1 minute, you will only allow, let's say, 100 attempts per minute, your whole system wide. In that case, the moment the attacker crosses the number 100 for their attacking attempt for your password brute forcing, your system will raise an alert and you will be able to flag that incident, and you can actively try block all those IP addresses. You can try showing CAPTCHA to all your users to filter out all the genuine users from the malicious users, etc., etc. Using this layered approach of rate limiting, you can prevent two things. attackers getting access to the account of a genuine user through brute forcing, and your servers crashing because the thousands of requests per second the attacker is sending to your server. So rate limiting is obviously a very important strategy whenever we are talking about security. We talked about authentication. Now it's turn for authorization. Again, if you want to go deep into authorization and the mechanics of it, please watch the authentication and authorization video separately. This is solely focused on the issues, the security issues related to authorization. And we already discussed the security issues related to authentication. To briefly explain, authorization basically means, while authentication means the identity of the user, to identify which row in our database, which row in the users table in our database is associated with the user who is trying to access our system currently. The same way, when we say authorization, it basically means after we have identified the user, after we know exactly which user we are talking about, the next step is what are the permissions of the user? What are the activities that the user is allowed to perform in our system, in our web app, and in turn in our backend? That's basically the difference between authentication and authorization. Now, the confusion, and when I say confusion, I don't mean the obvious confusion, which is confusing the definition between authentication and authorization. I'm pretty sure any engineer can easily understand what is the difference between these two. But the confusion that happens in our technical implementation between authentication and authorization, that's where most of these vulnerabilities arise, that is related to authorization. For example, I'll take a very realistic scenario that I often see in code bases. Most probably we have already discussed all these things, but we have a routing layer. This is the first entry point of our backend system. From routing layer, we go to handlers, which deals with things like request body parsing and validation and passing all the validated data to our service layer. And our service layer interacts with our repository layer. Okay. So usually what happens, we place our authentication middleware, which is like require auth, something like this. We place this at the routing layer after finding out which route the user is trying to access, because for login routes and for some of the public routes, we do not need the user to be authenticated. So depending on what routes the user is trying to access, we place this middleware which checks if it is stateful authentication, the presence of the cookie with the session ID and the validity of that. And in case of stateless authentication, it checks for the JWT token in the authorization header and the validity of that. If there is something wrong in there, it throws either 401, 403 back to the user, asking the user to properly authenticate. Now, this happens at the routing layer. After this point, what happens? The confusion arises here. The confusion is, once the user is authenticated, we have this false sense of security that now that we know the user is our own platform's user and we already have the data about the user, we have already authenticated the user. Now the user is allowed to access any parts of any of these systems, right? The handler, any kind of service, any kind of repository. Of course, we place some very obvious authorization related checks also at the routing layer, which is things like if the user is a member or the user is an admin or the user is a super admin, etc., etc. Or if we go a little bit more granular, if the user has access to the read permission on the entity books, if the user has access to write permission on the entity books, things like that. If we are going more granular on the authorization layer, okay, again, that is still at the routing layer, but the confusion, the security vulnerabilities that arise at the service and repository layer, because let's say at our routing layer, we have our require auth middleware, which properly authenticated the user. We checked that the user has a proper session ID in the cookie and the user is authenticated. In the next layer, we also check the authorization of the user, which is the user has the permission of read books. This is a granular permission which states that this particular user has the permission to have read access on the entity books in our database. Okay. Now, finally, we let the user pass. to our handler layer, service layer, repository layer. Now the API, the particular endpoint that the user is trying to access is this one, /books with a search parameter which says ID equals to something like 5. Now what is happening here in our web app, in our front end, we have an interface here where we are showing a list of books to the user, and there is a search bar here and there are some filters here, and in the filters there is one particular filter where they can pass multiple book IDs here, and we will only show the details of those books here. We will only show the books in the table which matches one of these IDs. Since the user selected or passed the ID 5 here, our front end made an API call, and this is the API for that, which is /books. In a search parameter, we are saying ID equals to 5. And this again, at the first entry level, it hit our routing layer. We check the authentication, check the authorization with the granular permission. And finally, in the service method, we call the repository layer. And this is the final query that we ran, which is select star from books where ID equals to, this is the final query we ran, and whatever the result that we got, we returned it back to our front end, and the user was able to see it here. Okay, that was the whole experience. Now the problem here is this part. The problem was this particular book ID, the book number 5. This is not a resource and not an entity which was created by the user, for which the user has access to. Which means the book 5 is not of this user, but since they pass this particular ID in the filter and we call the API, and since in the API layer we are not doing an authorization check, so what we should have done is, after this query we should have wrote and user ID equals to what is context dot user ID, whatever user ID that we were able to fetch at our authentication layer, we store it in our request context, and we have to match that in our database query to make sure that we only return the books for which the user has access to. Now, this is the kind of confusion that I am talking about. Just because the user was able to pass the authentication check, just because the user was able to pass the authorization check of having read access to books, does not mean they have access to all books in our system. So in our database layer, for every single query, we have to deliberately think what are the entities exactly that the user has access to. On a high level, because of this kind of confusion, a lot of authorization related vulnerabilities arise. So let's talk about a few famous ones for which we have already named those vulnerabilities. The first kind of vulnerability is broken object level authorization, or in short, BOLA. This vulnerability, which is called broken object level authorization, is exactly the scenario that I mentioned above, just a fancy way of describing it, which means that our system does not check the authorization of a user on entities on database level. It just checks the authentication and authorization during our routing layer, but does not check it at our repository layer. So that kind of scenario can cause this vulnerability, which is called broken object level authorization. Now, this scenario I explained sounds a little harmless, but someone with more technical knowledge, what they can do, they can write a script, they can iterate through all possible IDs of books in our system, but instead of books, it can also be invoices or payment related information in our database, and they can download every single invoice from our system. They can get a hold of all users' financial data, and they can also modify, they can also tamper with the invoice URLs, the account numbers, etc. A lot of damage can be done if we are not careful about broken object level authorization. So how do we actually fix this? How do we fix BOLA? As I have already mentioned, the fix is pretty simple, pretty intuitive, which means that even though we check authentication at the routing layer, even though we check authorization at the routing layer for entity level, which is read invoices, for example, in our repository layer, in our service layer, we also have to make another check, which means that don't just fetch invoice number 5. Don't just fetch book ID with ID 5. Fetch books or fetch invoices with ID 5, and where the created user ID or the user ID also matches the user ID that we were able to extract at the authentication layer, which means we stored the user ID in the context and we have to match that in our database query. So what we are saying, instead of just fetching the book with ID 5, we are fetching the book with ID 5, which also belongs to this user, or which also can be accessible to this user. We are mindful about authorization till the last point of access, which is the repository layer. We don't end up with our false sense of security from the routing layer. We have to take it all the way towards our repository. That's the way to prevent this broken authorization issue. Now, the second important thing, which is a very subtle thing here, is, and I have seen this in a lot of real world systems, is backend engineers, they try to provide a very good user experience because they are only thinking about the happy path, about their own front end. They don't entertain the scenario of an attacker trying all these combinations. So some engineers, what they do when they get an API request, let's say with invoice ID 5, an API which is supposed to fetch the invoice details with the ID 5. So what they do, they try to fetch the invoice details with some kind of DB query, db.query something, and they find this particular invoice entity. Then at the next step, what they do, they check if the context.user is equals to invoice.user ID. They have this condition. If this condition does not match, they throw an 403 error, which means forbidden. Now, technically, this is right. We are supposed to throw 403 errors, forbidden errors, whenever we have an issue related to authorization, whenever we have an issue related to a user not having access to a particular entity. But the problem with this is, if we return 403, if we return this particular response which is forbidden, we are confirming the fact that this particular invoice, the invoice number 5, which the attacker, if they have malicious intention, they most likely have guessed. They don't know for sure that this particular ID exists or not. They have guessed this ID and they're trying to verify if they can get access to this invoice, or at least they can make sure this particular invoice exists in our system, so that they have other ways to get an access to it. The moment we throw a forbidden error, we are saying that this particular invoice exists in our system, but we will not give you access to that. Even though you did prevent an attack there, but you also did some amount of information leakage, which can also be destructive over the long run. Because if you are following this pattern, then an attacker can come up with a list of IDs, 5, 17, 18, whatever, a list of IDs, and they can enumerate. They can call your API in a loop and they can find out these are all the invoices that exist in the system, so that they can go ahead and plan another layer of attack, something like social engineering, which involves interacting with humans, fooling humans, and tricking humans into extracting sensitive details from our system. And that is the reason another important point that we have to keep in mind is, when it comes to authorization related checks, we have to be a little more reserved about it. So ideally, in this scenario, when we get a API call for an invoice with ID 7, ideally what we should check, instead of checking the existence of this invoice in one database query and then checking if the user has access or not, then throwing a 403 forbidden error, instead of doing all this, simply what we can do is we just write a very simple SQL query, which is I select star from invoices where ID equals to 7 and user ID equals to whatever context.user ID. And when we run this, since this particular invoice, this does not belong to this user, what we'll get? No rows. And when we get no rows error, by default, what we do, we return a 404, which is not found response code back to our client. And since we return not found as a response for this particular query, the attacker, they cannot tell the difference between an invoice that does not exist in our system versus an invoice that exists in our system but that belongs to someone else. If they can make sure, if they can verify point number 2, they can resort to other layers of attack, which is mostly social engineering. But now that they cannot differentiate between these two, they cannot tell if the invoice exists in our database in the first place, which in turn helps preventing the other layers of attack, since we stop them at the root level without giving them any kind of information. Now, this whole thing, this authorization check database query level, this needs to happen not just for select queries, not just for view queries where we are returning information. This needs to happen for any kind of database query, which is either edit, which means update, or delete, or insert, any kind of database query that we run. We need to check this authorization of the user at the database level without leaking any information. That is also an important. Now, another similar vulnerability here is broken function level authorization. Now, this is pretty much similar to the above vulnerability, which is BOLA, an object level authorization, but this has a different angle. So this is more about restricting the access to functions as compared to restricting the access to data, which is about BOLA. BFLA is about functions. And what kind of functions do we mean? Are sensitive functions, especially the functions which are only supposed to be accessed by our admins. Let's say we have an endpoint, which is something like /admin/invoices again. Now, this particular endpoint is only supposed to be accessed by the site admin so that they can review different invoices. They can provide support to the clients whenever there is some kind of issue related to an invoice. Now, for this particular endpoint, we cannot do this, which is this pattern, select star from invoices. We cannot put a condition here, which is where ID equals to 5, user ID equals to context dot. We cannot do that here because the admin needs to see all the invoices of our system. There should be no where condition. Even if there is a where condition, it should be only for filtering like active invoices or pending invoices, etc., etc. There should be no authorization related checks here. For that reason, this is not a object authorization related vulnerability. This is a function authorization vulnerability, which means that let's say we have an admin panel here, and in this admin panel, we are listing all the invoices by using this above API, which fetches all the invoices of our system and shows it to our admin. Now, one clever trick that we did was we did not share this URL, which is safe.web.app. Whatever your URL is, you did not share this particular URL with anyone. Only the admin knows this URL. But apart from that, you don't have any other kind of security mechanism here. If the admin knows this URL, and as long as the admin is a user of our platform, they can go into the admin panel, they can log in as usual. The login flow is same for a regular member and the admin. The only difference is the URL, the access to the URL. Once any user is able to log in into the admin panel, they can call this particular API and they will be able to see all the invoices of our system. Now, again, this sounds a little stupid, but these kinds of vulnerabilities still happen in legacy systems where people try to provide security through obscurity. This is a very famous phrase in the world of web security, which means that instead of providing actual security, instead of providing robust security, what to do, you just hide information, you just do clever tricks, and you just do a lot of assumptions, and you just feel this false sense of security that your system cannot be accessed by malicious users or attackers. This is exactly the same case. Just by assuming that no other user has access or knowledge about this URL, our API is safe or our admin panel is safe. That is not the case. This whole setup can backfire as long as someone monitors your internet traffic, and the moment they see this particular URL and they find out that there are no admin level checks in your system, they can call this API independently and they can get a hold of all of your invoices in your system. The mitigation to this is something that we have already discussed. The routing layer, we perform authentication, and after authentication, we also need to perform authorization. And in the authorization, we not just check the granular permissions, in this case, which is read invoices, which is in our case true. A user who is trying to access their invoices, they also have read invoices permission, and a user who is trying to access all information, which is the admin level function, they will also have this same permission, is read invoices. The only difference is the user role. So this user is a normal user, which is something like member, and the admin will have a role something like admin. So another middleware should be present here, not just our permission middleware, also the role middleware, which makes sure that the user that is requesting access to this function, which is requesting access to this particular API, has the role of admin. They are authorized to access this particular API as admin. Then only we let them them call this function, and then only we return all the invoices of our system. That is how we prevent broken function level authorization. Another interesting vulnerability here is indirect object references and broken access control patterns, which talks about using sequential IDs of your database, which is something like 1001, 1002, 1003, and using these in your APIs, something like /invoices /1002 to fetch the invoice information of this particular invoice. Using this pattern enables attackers to guess all the other invoices in our system, the existence of all the other 1001 and 1003, 1009, and so on. Since our IDs are sequential, since they are predictable, they are prone to all kinds of attacks, all kinds of enumeration based attacks. As long as the attacker can predict the existence of all these invoices in our system, they can plan more number of attacks targeting these. One prevention to this is using UUID as our primary key, which looks something like this right here. These are randomly generated and often used as database primary keys. They're also URL friendly, etc., etc. But using UUID also comes with a couple of performance related issue that you have to read about. But generally, UUIDs are recommended for this. Okay, now that we have discussed all this stuff about authorization, try to cover two summarizing points which will cover all these vulnerabilities in a very simple manner. After discussing all these vulnerabilities related to authorization, we can categorize the authorization related attacks into two types. One is horizontal authorization attacks, the other one is vertical attacks. Now this is a very simple mental model, a very simple mental framework that you can use. Instead of memorizing all these different vulnerabilities related to authorization, you can just think it in a very intuitive way. First is horizontal. Now, horizontal authorization attacks involve user A getting access to the resources of user B due to some incapability, some kind of negligence in our system. It usually happens because we ignore authorization at the database level. And we call it horizontal authorization attack because the scope widens here. We are talking about different users. The scope widens here at our system level. That is one kind of attack. And under this, we have a broken object level authorization that we have discussed. And this is also called IDOR, something like indirect object reference. Both of them mean the same thing. Now, what is vertical authorization attack? This is the other case that we discussed, which is BFLA, which means a user after entering into our system, instead of widening their scope horizontally, what they do at our system level, they widen their scope vertically, which means getting access to more of our system's resource instead of other users, which was the case when we talked about admin level scenario. So after entering into our system, a user is able to get access to the functions, sensitive functions, which are only accessible to an admin user. So these are the two categories of authorization related attacks that we just discussed. Now, to discuss the framework, how do we actually mitigate, how do we actually prevent all these authorization related attacks? First thing is you need to centralize your authorization logic. You should not scatter your authorization related checks throughout your code base where they will be applied inconsistently or they are prone to getting forgotten. So you should have a clear authorization layer from where every single request passes through. Right? All your logic related to authorization should live in the same place so that it is easy to understand by all engineers in your team, and it is easy to maintain, and it is easy to scale. Second thing is a very simple framework which is called default deny, which basically means that once you have your authorization layer, the framework that you should follow is if your authorization logic does not explicitly allow something, does not explicitly allow certain permission, certain user role or whatever, then you should by default deny it. Instead of checking the other way around, you should deny any other kind of conditions which is not explicitly allowed in your logic. This way, what happens when you add new resources in your database or new endpoints in your routing layer, they are protected by default. Even though you forget to grant access to them in your authorization layer, but until you do that, they are protected by default. That is a very important safety mechanism. Third thing, test authorization specifically, which means that don't just test your happy paths. A normal user, a benign user, a genuine user is able to go through the whole workflow correctly and you move on from there. That is not how you should be building systems. You should also test for the edge cases, which means that user A should not be able to access the resources of user B. Same way, a regular member role user should not be able to access the functions of a user with the role of admin, or an unauthenticated user should not be able to access any kind of authenticated resources in your system, and should not test these things manually. You should have automated tests in your system, a dedicated test suite just for authentication and authorization, which checks for all these use cases. Because if you test all these scenarios manually, most likely there will be some change in your system someday, which will break one of these functionalities. And since you are manually testing all these things, it cannot be as comprehensive as automated tests, and you'll miss one of these scenarios, and that will leave a huge security hole in your system. If you have an automated test suite, every time a new change is added to your system, in your CI/CD pipeline, all these authentication and authorization related test suites are run, and you can be rest assured that your system is still secure as the day you build your authentication and authorization system, no matter how many additional changes are added to your system over the time. And the last thing is audit logs. Every time a sensitive resource, something like an admin endpoint, is accessed, you should log that in your audit table, that this particular endpoint was accessed at this timestamp by this particular user, etc., etc. Same way, every time an authorization check fails, when a user tries to access the resources of user B, you should flag that incident and you should log that as a breach event dedicatedly. Because if there is someone who's trying to probe your system, if there is someone who is trying to break your system, you should have the knowledge of that so that you can take advanced preventive measures for those. Okay. Now that pretty much covers all the things that you should know when it comes to authentication and authorization. Moving on to our next major vulnerability, which is XSS. It stands for cross-site scripting. Now we are going to see a small demo of this towards the end of this video. So before that, we'll just briefly explain what this vulnerability means and how does it work and how to prevent it. And we'll actually see it live in the demo. To explain cross-site scripting, it means that when a malicious user or an attacker, they manage to get their JavaScript, any JavaScript code or any JavaScript snippet, to execute in a user's browser, in a genuine user's browser, in the context of your platform, in the context of your front end, then this whole attack is called cross-site scripting. It's still not clear how does it work and why it is so dangerous. Let's cover that part first. Why is it actually dangerous? So we all know that everything that happens in our browser, all the processing that happens to JavaScript, any kind of computation that runs. And JavaScript in the context of a browser can do a lot of things. It can read everything that is happening on a page as long as it has the context of that page, including the sensitive data. It can also make API requests to a remote server by impersonating as the logged in user, because they have access to the cookie, they have access to the local storage. As long as it is not HTTP only, they have access to the cookie. They can also redirect the user to other pages like phishing pages, to phish the credentials of the user. And lastly, they can also alter, or they can also change the content of the page to trick a genuine user into thinking the website that they are looking at is a completely different website. To summarize, if an attacker manages to run their code, their JavaScript code, in another user's browser, exactly as it sounds like, it can be very destructive. Let's look at how this is possible in the first place. The first kind of XSS attack that we can talk about is stored XSS. And this is how it works. Let's say you have a blogging platform, and in that platform, you have a discussion board, a common system discussion board, where users can come and they can post their comments, and other users can reply to that comment, etc., etc. So if you are aware of how markdown rendering works in SPS or in client-side JavaScript-based applications, usually if we want to support markdown in some kind of input, then what happens? The user writes their comment in markdown. Let's say they use a hashtag to start a heading. So that this is a comment. Then they use hyphens to write bullet points, etc., etc. And when we preview this, or when we try to render this as markdown, what we do, we use these libraries. If we are talking about the React ecosystem, the most popular client-side libraries for interactive web apps, then what happens, this gets converted into HTML using different libraries like Remark, Rehype, and they have a plugin based architecture, so you can customize how this looks and how to style it, etc., etc. But this is the whole idea. The user writes their markdown in the input, and to show that markdown, you convert it to HTML and you provide some kind of styling, and you render that HTML by injecting the HTML directly into your DOM node. So we just take that and inject it whatever in a div or something like that, and whatever the user has typed. Bullet points, they will be converted to something like lists. So an unordered list, starting the tag here, li first point, li second point, etc. Then closing the unordered list tag here. So the markdown gets converted to this particular HTML, and we actually have to go ahead and inject this into the DOM so that it can be rendered and we can see what the user intended us to see. Even though if you are using these popular libraries like Remark, Rehype, and React, all the safety mechanisms are already taken care of. But assuming that you are in a scenario where you are doing all of this yourself, or maybe we are talking about a legacy system where the user types some kind of markdown or some kind of HTML and you render it by injecting that into the web page, and to store it, you send the whole converted HTML to your server, and the server in our database, and the next time the server fetches, the server sends it back, and the client injects that and shows us in the comment list. Now, a malicious user, what they can do, if they want somehow by tampering with the behavior of this markdown to HTML conversion and finding a hole somewhere, they are able to inject a script tag somewhere inside the HTML. And since we are taking the whole thing and injecting into the DOM, what happens, this script tag, it starts getting executed as genuine JavaScript code in the context of our platform, since that's where this script is injected. And that is the reason, if you take a look at React and search for dangerously set inner HTML, come here in the docs, as you can see, in order to render this particular HTML, what you have to do in React is you have to pass the HTML string inside a attribute which is called dangerously set inner HTML. The React team has intentionally set the name in a way that you are always warned that when you are setting HTML like this, you are on your own and you have to be careful about XSS attacks, since there is a possibility that you are injecting scripts into your web app. So this particular vulnerability happens not because of this practice for injecting HTML into the DOM. That has to be done if you want to render user defined markup in our web app, then we have to do some kind of injection. But to prevent that, what we should have done, what the server should do is, when the server receives this particular markdown, this particular markup structure that the user has typed in the form of a comment, it has to do a step of sanitization, which means it has to look for signs detecting if this can be a potential exploit, something like the presence of script tag, etc., etc. So the server can detect if a script tag is present and it can strip that off and only save the HTML. If the server does not do that, then your web app, your platform is prone to an XSS attack, especially a stored XSS attack, because every user who ends up viewing that particular comment, the script tag will start running in their browser. Now, the moment the script starts running in their browser, the attacker who has written the script, they can send all their session cookies, all their local storage information to a server which is controlled by the attacker, and they can view all those sessions, and they can, if they want, hijack those sessions also, or they can also redirect the user to a phishing page and steal their credentials. So there is a lot of damage that can be done here. So you have to be very careful about whenever you are injecting HTML structure into your web app, and you have to make sure that when you're storing that user provided markup, you are doing proper sanitization. There are also different types of XSS called reflected XSS, which deals with rendering the script tag in your URL. There is also DOM-based XSS, which is pretty much the same as the scenario that we just discussed, setting the inner HTML property of your web app. But to summarize, all these different kinds of XSS attacks, the cross-site scripting attacks, all of them happen for a single reason. The root cause for all of these vulnerabilities is user-defined content being treated as code rather than data. Again, this is similar to SQL injection attack, where the vulnerabilities happen because of the confusion between code and data. And XSS is pretty much the same, but instead of happening at the server layer, instead of happening at the SQL or database layer, it happens in the user's browser. When a user provided data, when put into a particular language's context, in this case, our HTML and JavaScript combined, gets treated as code instead of what it was meant for, which is data. That is exactly when XSS attacks arise. The easy prevention for this is obviously sanitization in your validation layer. So make sure whatever user provided content that you are dealing with, that you are storing, you are properly sanitizing it before storing it in your database. The point appears here again that every time you are dealing with user provided content, it does not matter whether it is a user provided search query, it does not matter whether it is user provided HTML or an image, which can be of a very big size. Every time you are getting something from the user, either you are storing it in case of this, or you are processing it using your database, or you are doing some kind of file handling. Every time you are dealing with users data, you have to be very mindful, very careful about how you are handling it, what kind of access you are giving, what kind of resources you are spending on this particular operation. If you do that, then you can get out of 99% of vulnerabilities very easily. Another prevention here, another technical prevention is CSP, is also called as content security policy. Now, content security policy is provided by your browsers. This is an HTTP header which is sent by your server back to your browser. And the purpose of this particular HTTP header is your server tells your browser exactly what kind of resources it is supposed to execute and what kind of resources it is supposed to block. Okay? Very clear instructions about the what kind of resources it can actually start executing, what kind of resources it should trust. So you can specify using a server things like only run scripts from these specific sources, from these specific domains, which are coming from our domains. Or you can specify that don't run inline scripts at all. No inline script, which means our earlier attack, which was caused by injecting a script into our DOM, this will completely get blocked. Since you're saying that don't run any kind of inline scripts in the context of our web app. So using CSP is also a very robust fix for these kinds of situations for dealing with XSS attacks. You can also specify from what domains you are supposed to load images from. If the images are from a different domain, then you'll also get an error from CSP. So that even if a malicious user is able to inject some kind of script tag into your browser, the browser will block it immediately. It will not let it run in that context at all. Now, one thing to focus here is the CSP, the content security policy that is provided. This is not actually a prevention. This is just one way to fight if you have any kind of XSS vulnerability. The core reason for which your site is vulnerable to XSS, that you have to fix yourself first by properly sanitizing your user provided inputs and everything. But CSP is configured just in case you forgot, just in case there was a very remote edge case which let an XSS attack to pass through. In that case, CSP can your last line of defense, but it is definitely not a prevention. So you should be doing all kinds of prevention, and in the end, you should trust CSP to block any kind of attacks that passes through all your defenses. There is another category of attack which is called CSRF, also known as cross-site request forgery. And I just want to mention this very briefly because in my opinion, CSRF is not a major threat to modern web applications. We cannot say that this is non-existence because we still have legacy systems. We still have outdated practices in a lot of systems. But as long as you are working with latest technologies and using decent libraries and frameworks, most likely you are not going to face CSRF attacks. But just to cover it in theory, CSRF works because of the cross-site nature of cookies, basically. When you visit a particular website, what happens? Your browser stores cookies for that site, this particular website. And when you make a request to that site, your browser automatically includes those cookies in the next request. And this whole thing happens even if the request originates from a different site. For example, if we take a realistic destructive scenario, you are logged into your bank's site and your browser, it has a cookie for, let's say, bank.com. And now when you visit another site, which is a malicious site created by an attacker, and the domain is evil.com, either through a phishing link or any kind of genuine web browsing. And when you land in this particular website, there will be a form which will get auto submitted, or there might be some kind of image tag with an URL that triggers some kind of JavaScript which submits the form for you. Now this evil.com, it will trigger a code snippet where evil.com is making a request to bank.com. And since it is your browser which is making the request to bank.com, even though the context is evil.com, from where you are originating this request from, but it is still your browser. And that is the reason your browser will include the cookie for bank.com in this particular request. And since the cookie was included, the server of bank.com, it will see the request as a genuine request and it will let it get through. And by using this whole workflow, the malicious user, the one who created evil.com, they can perform some kind of destructive actions. But again, as I have already mentioned, CSRF is not one of the major threats that you should be worrying about as long as you are using modern technologies and modern libraries. Another reason I say this is not a major threat is because the same site cookie config that we discussed in the authentication section, where it is recommended that you always set this either as strict, or if your front-end or back-end are in different domains, you can set it as lax. By default, our modern browsers set the same site config as lax. And unless your same site config is none, you're by default protected against the CSRF attacks. And the next point of defense is our CORS config. Now, CORS is definitely not a security mechanism, but using CORS, what happens typically are backends, they have CORS configs and it checks if the request that we are receiving, it is coming from a request that is own frontend. If it is not, then we do not set the CORS header and the browser of the client blocks that particular request. Now that is another not a very robust prevention, but it is still a line of defense against CSRF attacks. So that's one of the reasons worrying about CSRF attacks does not make a lot of sense, at least with our current technologies, libraries, and frameworks. So we are just going to mention it briefly and move on from here to the next section. So far, we have mentioned and discussed different kinds of vulnerabilities, how they work and how to prevent them, etc., etc. Lastly, we will discuss a few practices which can turn destructive, which can create security holes in your system, and how to prevent those and how to think about those. The first thing is misconfiguration. Misconfiguration in your system can also open a lot of security holes. For example, let's talk about secrets management, the most abused concept in backend, secrets management. And when we say secrets, we mean things like API keys or database passwords or encryption keys or JWT or whatever technology that we are using, or authentication secrets, auth secret. So one obvious security vulnerability is, which I don't think anyone does these days, is storing any kind of secret in our source code, right? Which gets committed into Git, and that in turn lands in GitHub or Bitbucket or GitLab, whatever version control system that you're using. And the moment that happens, everyone who has access to your GitHub repository, your Bitbucket repository, or your GitLab repository, they can now see all your secrets. They can access your database, they can access all your external services using the API keys. They can also mess with users' data using the authentication secrets and the encryption keys. So making sure all your secrets always live in environment variables, either using things like .env or using some kind of external secret management, AWS parameter store, or Vault is from HashiCorp, etc. There are a lot of services these days. So always make sure any kind of secret does not go into your version control system. Even if a secret gets leaked into your VCS or your GitHub and you go ahead and delete that, that is still in your commit history. Someone who goes back in the commit history, they can still access that particular secret. So the moment you accidentally commit your secret into your VCS, into GitHub, you should go ahead and rotate that secret or delete that secret and create a new one. Okay? One of those things that you have to keep in mind when you're talking about security. The second kind of misconfiguration that we should talk about is debug mode in production, in our live environment. Typically, when we are developing in our local, writing code in our local, our logging mode is set at debug level. What that means is we log all kinds of data in our standard output. Things like very detailed error messages with stack traces. Now, stack traces itself contain a lot of information about how our functions are named, how our files are named, how our code is structured, etc. Same way, we also print a lot of information about our databases, things like the explicit SQL query, the database field configs, the database transaction related information, all these things that get printed in our local standard output or in our local terminal. Ideally, when we go to production, the log level is set to info, which means we only log the information related stuff for our production server, which means all these things, the error stacks, the database query logs, and the whatever debug logs that we are printing, for example, users sensitive information, etc., all these things, they never show up in production logs. They are only meant for our local. As long as our log level is set to debug, that's only when they'll show up. Otherwise, they'll never get printed. But if we don't configure the log level specifically at info level, and anything which is not debug level in our production, in our live environment, all these information are going to show up in our logs. And if and when production logs get breached, the attacker can get a lot of information about how our code is structured, what are the sensitive data about the user, what is the sensitive data about database, etc. So it is important that you are mindful about your log levels. What is the log level of your production environment? What is the log level of your local environment? And what is the log level of your staging environment? That is another misconfiguration that can cause a security hole in your system. The third one is security headers. Now, when it comes to security headers, we have already talked about CSPs, which tell your clients what kind of JavaScript it can execute in your platform's context. There are some other HTTP headers which help us prevent a lot of security related issues. Things like frame options, which when properly configured, it prevents other websites to embed our website inside an iframe, and which in turn helps our users from being the victim of phishing attacks. Because if we do not properly configure X-frame options, an attacker can configure our website and they can show our website inside an iframe, but using a technique called clickjacking or any kind of other JavaScript code that is running behind the scenes, they can capture the user's credentials and they can do a lot of stuff depending on the user's interaction on that site. Since the site itself is in control of the attacker, but in a separate iframe, they are hosting our website. there are a lot of different kinds of attacks that can be planned there. Similarly, there are other security headers, and these days pretty much all the web frameworks, does not matter whether you're using Node.js, Express, or Golang, Echo, Gin, Python, Django, whatever web server framework that you're using, all of them provide radio security middlewares, which when configured is just a one-line change. All these industry standard security headers are configured for you. You don't have to manually configure each of them as long as you use these modern middlewares. So that's pretty much all that I wanted to discuss about security in the context of backend. Now, finally, putting all of this into perspective, what I want to say is every vulnerability that we talked about, and there are others, there are hundreds and thousands other vulnerabilities, they're all about the same fundamental thing, which is boundaries. So data crossing boundaries between systems or between privilege levels, between programming languages, between different markup structures, any kind of boundary, whenever data crosses any of these boundaries or any of these trust zones, you have to be very careful. We have to be very mindful about what exactly is happening in your system, because every time we have crossed a boundary, that's when we have encountered a vulnerability. For example, things like SQL injection, where untrusted input coming from the user that crossed into the boundary of our database query language. Same way when we were talking about XSS, cross-site scripting, that crossed the boundary of users markdown into the boundary of HTML. Same way for broken authorization, the requests cross the boundary of what different users should access. So the tip here is every time you're writing code, ask yourself, where is data crossing a boundary? What assumptions am I making about the data? And what if those assumptions are wrong? If you ask yourself these three questions repeatedly every time you encounter data crossing boundaries, then I can promise you that you can avoid 99% of the vulnerabilities that modern backend applications suffer from. And another thing is, no single kind of defense is perfect. So you always have to think in layers. For example, your first layer of defense, and this I have stressed in so many videos, it should be input validation. Always validate every single thing that is coming into your system, which is the first entry point for your backend, which happens after the route is matched. At that point, you have to strictly validate every single thing with as many conditions as possible. The final data that leaves your validation layer and reaches your handler layer, it should be in exactly the structure that you expect it to be. There should be no surprises from that point on. That is your first line of defense. The second is parameterized operations. Always use APIs that provide explicit parameters, whether we are talking about databases or we are talking about OS level functions like file operations, etc., etc. Always use predefined, framework defined, or your programming language defined functions instead of just constructing the commands by string concatenation. Then authorization checks. Verify every access at the point of access. Since for the broken object level authorization vulnerability, what we did, we verified the authorization of the user at the routing layer, but the actual access was at the repository layer. And that's why the vulnerabilities happened there. So always verify the access at the point of access. You have to be mindful about where exactly the authorization point of access is, and you have to check the access there instead of a couple of layers upstream. Then security headers and policies. You have to configure your browsers and your servers so that they can limit the damage in case something fails. For example, things like CORS, CSP, and security headers, all these things, they are not very robust defense mechanisms, but in case some kind of attack passes through your first line of defenses, then these secondary mechanisms can help you tone down the scope of the attack. Then monitoring and logging. Always monitor any kind of suspicious activity and log them properly. Send them to your logging service, raise alerts, etc., etc. That should be very obvious. And the whole point of this is, maybe there can be some kind of weakness in one of these layers, but if you have multiple layers of this security, then An attacker has to bypass all these layers at once before they can cause any harm to your system, which has very less amount of chances. So the last thing that I want to mention is security is not about learning a couple of techniques or a feature that you just learn and go and implement. Security is more about being paranoid about your systems and the mindset that you bring before writing every single line of code. So always think about boundaries, always think about assumptions. And one last thing that I want to mention here is if you want to learn more about security, explore in depth, there are two resources that you can take a look at. First thing is Fort Sugar Academy. Now, this is the company that has created the tool which is called Burp Suite, which is a very famous ethical hacking tool, penetration testing tool. And this Portsugar Academy has a very comprehensive catalog about a lot of vulnerabilities, how they work with practical labs and the theory behind it, the computer science behind it, and everything. You can also recognize a lot of vulnerabilities that we talked about, things like SQL injection, cross-site scripting, CSRF, and clickjacking, CORS, SSRF, and OS command injection that we talked about. So authentication related vulnerabilities, OAuth related vulnerabilities, JWT attacks, and a lot more that is beyond a video like this that you can explore here. And the best part is all of this is completely free. There are no charges, no hidden charges here. I have personally learned a lot about web security and security in general from this particular resource. So I hope you can spend some time and learn more, way more than what I was able to cover in this particular video. Then we have OWASP, a security focused foundation, and OWASP top 10 vulnerabilities. It is a very famous list of current set of vulnerabilities that modern systems suffer from. They keep publishing this list every few years. So the current list is something like this. On the top, we have broken access control, which covers things like BOLA, BFLA, all these things that we talked about. There is security misconfiguration that we discussed, and an injection, which covers OS command level injection, SQL injection, and a lot of vulnerabilities and how severe they are, the real world instances of those, all of them are listed here. Now, there is a resource called OWASP cheat sheet, which is again a very good resource that you can take a look at to learn about a specific concept. For example, if we go to, let's say, authentication here, then you'll find a lot of information about what are the good practices that you should follow during authentication, what are the bad practices, what are the security threats that you should be aware of. And they cover a wide variety of domains when it comes to security. Let's say if you go to session management, then here you'll find a lot of important information, a lot of useful information about what are the best practices, what are the industry standards that you should follow while working with sessions, how to manage sessions, the importance of session ID, why it has to be a cryptographically secure pseudo random number generator, what are the conflicts of that, and a lot more information. You can find a lot of information for a lot of security related stuff. I have personally gone through all of these multiple times over the years, and this has been excellent in building the security mindset by covering different domains, by keeping a single goal in mind, which is security. But coming at security from different domains, that opens up a completely new perspective in your mind. So just wanted to share these two resources with you, because of course this video by no means is comprehensive. Security, as I have already mentioned, is a very huge concept, very huge domain. The goal of this video was just to make you aware of some of the things that you should think about while building your backend. And I have shared these resources so that you can independently do a lot more reading on security and understand these concepts a lot more deeply, better than I was able to explain. Okay, that's pretty much all I had to say about security, and that's it for this video.